the sequence of functions from R to R. So there should be, in fact, a subscript, but I will usually omit the subscript and just call it det. And det of a 1 by 1 matrix is just the entry. Det of a 2 by 2 matrix is familiar expression. And what we did was we defined det of an n by n matrix inductively where a minus 1, 1, a minus 2, 1, these are all n minus 1 cross n minus 1 matrices, which I will not repeat the definition of. So inductive definition, determinant of an n by n matrix is defined in terms of the determinant of an n minus 1 cross n minus 1 matrix. So this is an inductive definition. And we proved, well, I didn't prove it, but these are the most important three properties: that the determinant of the identity matrix is 1, and if determinant of so here you're writing an n by n matrix as a column vector, each of whose entries is a row. So this is the n cross 1 column vector. R1, R2, Rn are 1 cross n row vectors. And so this is the first property, this is the second property, and the third property is that determinant of a n cross n matrix where two of the rows are equal, two adjacent rows are equal to 0 if Rj is the same equal to the Rj plus 1 row. Then I stated a bunch of proposition, properties in a proposition, so which is quite long. So I will not repeat the proposition. But let me see. Yeah. So, but let's say what the content of the proposition is. So the proposition says let D be any function from n cross 1 matrices to R, any function that satisfies 1, 2, and 3 as above. then it satisfies about 9 other properties, 1, 2, up to 9, okay, which I will not write down. Now, I'm just trying to figure out if there is a way of actually. Okay, I think I have. I can just show you. Excellent. Yeah. Here is a proposition. I hope you can see it. Okay, very good. So it says that if a multiple of one row is added to an adjacent row, the value of D is unchanged. If two adjacent rows are interchanged, D changes sign. If any two rows are equal, D vanishes. So note that earlier we proved that for the determinant, if two adjacent rows are equal, D vanishes. So we are assuming that for D also. So D is a function which has a property that if two adjacent rows are equal, D vanishes. And now property 3 of the part 3 of the proposition says if two rows are equal, whether they are adjacent or not, D vanishes. And now 4 is a strengthening of 2. It says if the multiple of one row is added to another row, even if they are not adjacent, the value of D is unchanged. And 5 is a strengthening of 2. If two rows are interchanged, D changes sign. And finally, 6 says if any row is 0, D vanishes. Okay, so these are all properties. And actually, I don't think I will prove any of them, but let me just prove one of them, okay? Yeah, just, yeah. Okay. Okay, let me prove okay. So what is property 1? If so adjacent is important, then the value of D does not change. So let us prove this. Proof. So what does this mean? I take a matrix n by 1 matrix, which is of this form R1 tilde, R2 tilde, Rj tilde, Rj tilde plus 1, Rn tilde. And supposing I add a scalar times the j plus 1th row to the jth row. Okay, I will need more room, so let me make. So R1 tilde doesn't change, R2 does, the second row doesn't change, and what happens is that the jth row changes to lambda times the j plus 1th row. I am plus the original row. Okay. So this is what I have done. a multiple of one row is added to an adjacent row. So here I have taken lambda times this row and added it to this row. That is what's happened. So here the difference is here. The difference between these two matrices happens on the jth row, because I've taken to go from here to here, I've multiplied the j plus 1th row by lambda and added it to this. So that is how I get this. Okay. And what does part 1 of the proposition say? It says that if you have any function d that satisfies properties proved for determinant in the theorem, will have the property that d of this matrix is equal to the d of this matrix. That is what, so we need to prove this, to prove, and if you to prove this. Okay, so let me make sure that you guys are following me. Is everybody okay with? I've not proved anything yet, but I've just set up the problem. Okay, yeah, I've just set up the problem. Is everybody with me? Rishabh, are you okay?
Yes, sir.
Yeah. So
yes, sir.
Yeah. So I need to prove the equality of the D in the last at the bottom of the screen to prove the first part of the proposition, which is here. Okay. So I need to prove, to prove this, I need to prove this. Okay, but I can only assume 1, 2, and 3 of the theorem. Okay, so I can assume these things. I can assume that what can I assume? So let me just say what I can assume. I can assume d of this is 0. I can assume this. I'm sorry. I don't like this. I don't like unnecessary colors. So I can assume this. I can assume this. And I can assume this. So let me, this is no longer a theorem. This is part of, so assumptions on the function D. So I assume that D satisfies these 3 properties, and then I have to prove this. So let us prove that. So D of R1 tilde, R2 tilde, Rj tilde plus lambda, Rj tilde prime, Rn equals D of R1 tilde, R2 tilde, Rj tilde, this should be 1 here, Rj tilde plus 1, this is Rj tilde plus 1, Rn tilde plus lambda times D of R1 tilde, R2 tilde, what? Rj tilde plus 1, Rj tilde plus 1, Rn tilde. This follows from this. I'm using this with lambda equal to 1. So this is actually lambda prime. Okay. Is this clear? Is this step clear to everyone? I'm just using separate linearity with respect to this row. Is this clear, Shakti?
Yes, sir.
Okay. But now this is equal to D of R1 tilde, Rj tilde, Rj tilde plus 1, dot, 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 Rn tilde plus. But what can you say about this? What can you say about this determinant? Then sorry, not this D. What have you assumed about D?
It will be.
It is 0.
It is 0 because we have assumed property 3. D vanishes if two adjacent rows are equal. Okay. So here the jth row is R. So these two rows are equal. Equal rows. Okay. So this is 0. So we have this equal this, which is what we needed to prove. Okay, so we have proved this. Okay. So each part of the proposition. So let us take a look at the proposition. It follows by similar tricks, but you have to prove them in this order. Otherwise, it will not be clear. But if you prove the statements in the order that they are stated in the proposition, you will just, it is like it is on kind of, the proof is on autopilot. You really don't have to think too much. It will be clear what to do as you go down up to 6. Okay, so I'm not going to prove 1 up to 6. Now let us see part 7 ABC. Now this is an important part. Okay, so skipping proofs of 1, so 2 to 6, we come to 7. Okay, 7 is in 3 parts. D of E equal to 1 if E is of first kind, D of E equal to -1 if E is of second kind. These are elementary matrices. And D of 1, 1, 1, C 1. So let me write this big. For an elementary matrix of the third kind, which I recall is a matrix of this kind, 1, 1, 1, except one of the diagonal entries is a non-zero scalar, and 1 and 0. is equal to C. Okay. So these are, I've just written out proposition 7. It tells you what is the value of D on elementary matrices. The point is that if you assume that D satisfies these properties, the Roman numeral 1 up to Roman numeral 3, then the value of D on elementary matrices is fixed. So why is that? Well, so let us look at, okay, let us, so let us look at, so let me call this A, B, and C. So C is the easiest part. C is the easiest. Okay. Proofs. I'll start with the easiest, with this C. Well, this is D of 1. Okay, I will just write this R1 tilde, R2 tilde. So this C is in the jth row. So I claim, okay, so basically the claim is that 1, 1, blah, 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 C1, where C occurs at the intersection of the jth row and the jth column, is like this: R1 tilde, R2 tilde, C, Rj tilde, Rn tilde. Sorry. Where I'm going to force you to think now. Okay, tell me what R1 tilde is. I'm taking this matrix and writing it in this form. So what should R1 tilde be?
So 1 followed by zeros.
Exactly. 1, 0, 0, 0, etc. And what about R2 tilde?
0, 1, and then all zeros.
Exactly. And this should have 1 on the jth place. And this should be 1. Okay. Is this clear? Remember, I am multiplying Rj tilde by C. That is why I can take Rj tilde to be, again, just 1 in the jth place. Shakti, is it okay?
Yes, sir.
Okay. So now, if I take determinant of this, sorry, not D, D of this, that's equal, that's the same as D of this. What does property 2 tell me? D of this is what?
P times D of R1, R2, Rj, R.
Very good. R1 tilde, R2 tilde, Rn tilde, right? But what is this matrix that this matrix I have written as a in the row vector form? What is that? This is just D of the identity matrix. Right? But we already know what is the value of D on the identity matrix? It's 1. So this is C into 1, which is C. Okay, so we prove that any function D that satisfies these Roman numeral properties 1 to 3 on an elementary matrix of the third kind has this form. Okay, now let us try elementary matrix of the second kind. So this is property B. Take an elementary matrix of the second kind. Do you remember what that is? That is of this kind. 1, 1. And what happens is that you pick a I and you pick a J, pick a I and a J, and you interchange the positions of 1, 0. So it's like this. Okay, so this is equal to, so see, okay, let me call these standard row matrices, row vectors R1 star, R2 star, Rj star, Rn star. Put a star here. So this matrix, tell me how to write this in terms of the R1 stars.
Sir, we're switching R1I and R1J's. Sorry, R I star and R star, J stars positions.
Very good. So this is equal to R1, Rj star, R1 star, Rn tilde, where this goes in the ith place and this goes in the jth place. So this matrix is got from the identity matrix by flipping the ith row and the jth row. Okay, but what was property, something that we've already proved. So let me just so we are already supposed to have proved properties 1 to 6, and property 5 says if any two rows are interchanged, D changes sign. So using property 5, proposition part 5 of the proposition, whose proof we have skipped, has been skipped. We see that D of this matrix 1, 1, 1, 1, 1 is minus D of the identity matrix. So this is the elementary matrix of the second kind. And similarly, you can prove A also. If E is of the first kind, it's D. I shouldn't say determinant, because we are talking about an arbitrary function D that satisfies Roman numeral property 1, Roman numeral property 2, and Roman numeral property 3. Okay, so I'm not going to prove part A. I leave the proof for you to check. Very good. So now that we have proved 7 also, now let's turn to part 8 of the proposition, which is here. So let me write it, okay? D of EA is D of E, D of A, if E is an elementary matrix and A is an arbitrary matrix. Okay, so one has to again prove this separately for the three kinds of elementary matrices. Okay, we must prove this for the three kinds of elementary matrices. I will only prove it for E of the second kind. Example, if E is of the second kind, EA, what is the relationship between A and EA? How do you describe EA in terms of A? We know this. We have already dealt with this.
We interchange two rows.
That's right. Yeah. So interchange two rows. That's what, if you take an n by n matrix and multiply it on the left by an elementary matrix of the second kind, the effect on the matrix A is that two rows get interchanged. The rows, which rows get interchanged depends on the elementary matrix. Okay. But so therefore, D of EA equals, well, we already proved that if two rows of a matrix are interchanged, then the value of D changes sign. That's one of the things that we skipped the proof of. So this is minus D of A, but minus 1 times D of A, but this is D of E if E is a elementary matrix of the second kind. So we have proved this. And similarly, other parts of the of 8 are proved exactly like that. So look again at 8. So here is 8. So you do this separately for each kind of elementary matrix. You take EA, describe in words how EA is related to A. For example, E is an elementary matrix of the second kind. EA is got from A by multiplying one particular row by a scalar C. And we already proved that if that happens, D of that new matrix is that scalar times the D of the old matrix. But D of that corresponding E is just C, that scalar itself. So you just go back and forth between sort of English and mathematics. So in other words, you take EA, say how the two matrices are related, and then you've already proved that if two matrices are related by that, how D is related. That will be related, that will give you a factor, and that factor will be the D of the corresponding elementary matrix. So this is the idea of the proof. So I'm assuming that we proved this. So now we come to part 9. If A, what does part 9 say? Yeah. If A is in row echelon form, either A is invertible and D of A is 1, or A is not invertible Well, this is easy because if A is in row echelon form, then the possibilities are A invertible, then A is just the identity matrix, and we already know that D of A is 1. A not invertible, last row is 0, and D of A is 0. Because if any row of a matrix is 0, we already shown that D of A is 0. Okay, so let me put up the proposition again here in all its glory and give you time to look at it for 2 minutes while I take a break, and then we will come back and take questions and go forward. Okay, so I'm back. You had time to look at the proposition. I'm going to go ahead now. We are going quite rapidly. I'm assuming you've been able to follow me. If there are, this is your chance to stop and ask questions. There are no questions, so I'm assuming I can go ahead. Very good. So, by the way, you are supposed to read these proofs carefully because you know, I will assume that you know the techniques and the arguments. Okay. So now comes a very important corollary that any function D that satisfies the properties 1 to 3 listed in the theorem is actually, there's only one such function, namely the determinant that we have already defined. Okay, so let me formulate it this way. There is only one function that satisfies 1, 2, 3, namely the determinant. So why? Well, so we use the fact that any matrix can be proof we have to show that any D satisfying 1, 2, 3 agrees with the determinant on all A. So given any A, we know there exists Ej minus 1, E1, such that Ej minus 1, E1, A equal to A definition is in row echelon form. So then D of Ej minus 1, E1, A equal to D A prime. But by what we have already proved about D, whenever I multiply on the left by an elementary matrix, you have this is equal to D Ej, D of the rest, and then you do it again. So this finally you get this is D Ej minus 1, blah, 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 D E1 equal to dA equal to dA prime. But we know that we've already determined the D of elementary matrices, and if you compare the list of Ds that we found, these are all equal to dit. Just let me I have to say this right, otherwise you will get confused and I'll get confused. 1 second. Yeah. See, on the other hand, the same thing holds for dit, because dit satisfies 1 to Roman numerals 1 to 3. So this is equal to dit of Ej A. Just give me a second. Sorry. Yeah. So now look at these two equations. So this, you see, so dit satisfies this equation because dit satisfies Roman numerals 1 to 3. D satisfies this equation because it also satisfies Roman numerals 1 to 3. On the other hand, on elementary matrices, these numbers are all equal to these numbers. And on row echelon matrices also, the value of D and dit agree. So this is equal to this. Therefore, this is equal to this. Is that clear? So I was a bit clumsy in framing the argument. but I think now it should be clear. But let me give Siddhant.
Yes, sir.
Yeah, so let me repeat. So, so start with the fact that any metrics can be brought into row echelon form by a sequence of row operations, or equivalently by multiplying by some sequence of elementary matrices. Okay, that is this condition. Now apply D to both sides of this equation and peel off these guys one by one, because we know that that is what happens with D. So we get this result. Now det also, because it satisfies 1 to 3, will satisfy this equation by exactly the same argument. But the value of det on elementary matrices is the value of D on elementary matrices for any D that satisfies 1 to 3. And the value of det on row echelon matrices is also the same as the value of D on row echelon matrices. Therefore, det has no choice but to agree with D. In other words, D has no choice but to agree with det on arbitrary A. So, in other words, there is a unique function D that satisfies det, unique function that satisfies properties 1 to 3, and it satisfies all these additional properties that we proved for the in the proposition. Okay, now finally we can prove something that we have known all along, but which would have been, of course, purely brute force computation can be done by using the Kramer's expression for the determinant. But here is now we can now reap the fruits of our labors, namely theorem. Dit is multiplicative, i.e. dit of AB is dit A times dit B.
Sir,
Yeah.
sir, for proving proposition 8.3, are we supposed to use only theorem 8.2?
Not theorem 8.2, properties 1 to 3.
Yes. Sir,
Yeah.
so
Yeah,
we're
yeah,
supposed to only that, right?
Only that. We assume
Okay,
that there a function D is given which satisfies properties 1 to 3, and then we prove the proposition. We are not
Okay.
using, yeah, because we don't know anything else about D other than that it satisfies properties 1 to 3.
Okay, sir.
Yeah, that is why the proposition is has such a strange statement. You first prove a weaker version of something that comes later.
Okay.
Okay? So it is, as I said in the last class, you have to frame it like that, and you have to prove it in that sequence. Otherwise, everything falls apart. It's slightly delicate machinery. It's stated in a certain sequence, and you have to prove it in that sequence. Otherwise, it doesn't even make sense, because why is it that in the same proposition, both a weaker form of and a stronger form both appear? That's because there's a logical sequence to that. Okay. Okay.
Okay, sir.
Now, yeah. So now the fact that det is multiplicative is very easy to prove. I will not prove it. It's the proof is there in the notes. Okay. Okay, so we are done with the determinant of an n by n matrix, and so now I still have some time. So now we have to prove something abstract and very important. So let V be an n-dimensional vector space linear its determinant det T. This will have the following property. One, det T is non-zero if and only if T is invertible, i.e. bijective. Two, det of S times T is det S times det T. Three, if V is M n cross 1 and A is n cross n matrix, det of A hat is det of A. So here, this det is determinant of n cross n matrix, already defined. And this is determinant of associated linear map M n cross 1 to M n cross 1. Okay, so what you must understand from all this is that if you are given any vector space, as long as it's finite dimensional, then there is a very natural function defined on the space of linear maps from the vector space to itself, which has exactly the same properties as the determinant of an n by n matrix, provided you interpret the n by n matrix as giving a linear map from column vectors of length n to column vectors of length n. And this is a very, very important thing. So, okay. So how would you do this? How would namely, how to associate to T V to V a number det T. Knowing what we know before, what we know about matrices. So, for example, let's do this example. Dim V equal to 1. Then you are given, and supposing I'm given a linear map from V to V. I have a one-dimensional vector space, and I have a linear map from the vector space to itself. What should be its determinant? Take your time, think about this. And this is, in fact, a good way of revising your understanding of what has happened in the course so far. Any thoughts?
Sir, I have a thought. Like T is linear, so any vector V in V goes to lambda V. So that of
Okay.
T is just lambda.
But if I take another vector, that could go to some lambda prime V.
Both has to be equal. Lambda equals to lambda prime.
Why is that?
Because wait, I need to think about.
Yeah.
Sir, hello, sir.
Yeah. Who is this?
Sir, this is Nilabjo.
Okay.
Sir, I think if T is 1, then only the lambda as proposed by Aryan would be unique.
Okay.
Otherwise,
Okay. Srimati, do you have any ideas? This is the price you pay for keeping your video on.
Yeah. I mean, I don't know. I think determinant T is equal to T. I mean, in the sense lambda, whatever lambda you multiply it with.
What lambda? I mean, because that was the issue with the earlier suggestion. No, if you take a vector V, first of all, why should T on that vector be lambda times V?
So, I mean, like whatever matrix you multiply V with, it should be.
Where is there is no matrix.
No, like a linear map.
V is just a vector space, n-dimensional vector space. There is no matrix.
No, I'm saying T, the associated with T, there's a matrix, right?
How?
No, so we showed this already.
No,
Like-
we haven't. Only for column vectors to column vectors.
So maybe I can try.
Yes, sir. Any element on the vector space can be written as a column vector, since it's if for finite dimensional vector space it's like we have a basis, so we can write it as a column vector. It's isomorphic to Rn.
Okay. So then yeah.
When we
very
find the
good.
matrix, and it can be shown that two matrix representation of the same linear transformation, both of their determinant will be the same.
Who said this?
Bijay and Rai.
Okay, you said probably it can be shown, or it can be okay. Now there is something in the chat.
So I think that's the similarity of matrices comes in. Like similar matrices have same determinant. That can easily be shown. Like
Yeah, but why? So suddenly you're bringing why are there two matrix representations of the linear transformation similar?
Because we just change from one basis to another basis, right, to get different matrix representation of the same linear transformation. So there has to be similar. So
you are feeding in a lot of your previous linear algebra knowledge, but perhaps yeah. So there is a suggestion from which came to me directly from Astana, that it's V is one-dimensional. So let's coming back to one-dimensional thing. He says there is a vector E such that all elements are given by so that is so there is one vector in such that all vectors are multiples of this vector. There is one basis, So let me just put everybody on the spot. I'm not going to give the answer. So this thing. So Srimati, so you see the point, no? Because there is something to be proved.
Yes.
Just given a vector space and a linear map, there is no matrix associated to it.
Yeah. I have to think about it. Yeah.
No, don't think about it.
No, but in this case, it's one-dimensional, right? So it is technically a column vector.
No, it is not. That way, any n-dimensional vector space can be thought of as a column vector, but there is a choice there. You have to choose a basis.
Oh, yeah.
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 So you choose a basis, then linear maps can be identified with matrices. And then you can take the determinant. But then that raises the question, supposing I choose a different basis, will I get the same determinant?
Yeah.
Right? That is not obvious at all.
Yes, sir.
You seem to think that this is this is not a pedantic point. I mean, but this is the crux of the matter. Somebody else also said something. Was it Debashish?
No, sir, I didn't mention anything.
Okay. So let me leave you here. I think I hope you know I keep
So I had a
leaving
different
you.
doubt, sir.
Yeah. Okay, very good.
The
So
few slides above.
I'm not going to go forward with this today, but we have a little time. So somebody who had a different doubt.
So me, sir, Debashish.
Okay, bole.
Sir, so why the determinant is the only unique map satisfying all those three properties?
So that is what I proved, no? Because you use row reduction. So let me run through the proof again.
Okay, sir.
So we know that any function that satisfies the three properties. Just give me 1 minute.
Yes, sir. Sure.
आप आज लेट आ रहे हैं क्या? अभी आए? पहले आ चुके हैं? Okay, thank you. नहीं, okay. So we proved that so can you see the screen? I've scrolled up to, yeah. So we proved that any matrix, any function D that satisfies those three properties satisfies a bunch of other properties, or in particular, dit also satisfies all the properties of the proposition. Remember that. So now take any A, we know that there exists a sequence of elementary matrices E1 to Ej, so that when I multiply A on the left by E1, then E2, etc., the corresponding matrix A prime is in row echelon form.
Yes, sir.
Now, we know that if I multiply any matrix by an elementary matrix, what happens? So I can go from here to here. So this D
the function. Okay.
is equal to this into this.
Yes, sir. Yes.
And by repeating, I know that this is equal to this.
Oh, yes, sir.
So I have this equation, and I have exactly the same equation for det. Because det satisfies properties 1 to 3. That is a particular example of a D.
Yes, sir.
Now, on the other hand, det and D take exactly the same values on elementary matrices and on row echelon matrices. So these values are all the same as these values, and this value is the same as this value. Therefore, this value must be the same as this value.
So, but isn't it? This is the inductively we have proved this statement.
Sorry,
have you proved this statement inductively?
How do you prove which statement? This statement?
Yeah, this is. Isn't this inductive proof of the statement that
no,
both
it is
the functions are equal?
No, this is an inductive proof of okay. I just we've already proved that when I take a matrix and multiply it by an elementary matrix, then I have this.
Yes, sir.
And then you keep doing that. Okay, it's an inductive proof. But it's a finite induction. So I can just keep doing it. For any j, I can just keep doing it. If you do it j times, you get here. So you really don't need serious induction.
Okay, sir.
Okay.
Yes. Yeah.
So D satisfies this. Det satisfies this. These values are all the same as these values. This value is the same as this value. Therefore, this value must be the same as this value.
Yes, sir. Yeah.
Okay, that is it. Okay, so let me please
I think I can
read
prove
these
it.
proofs. Yeah, go ahead. Was there another question?
So I think I can prove the dim one case. I mean,
You can prove, sorry,
the dim one case for TV1 to TV
who is
to
this?
V. So
Who is
this is
this?
Romit. So it's Romit.
Sorry.
So it's Romit. Should I start off
Okay.
today or just leave it for tomorrow?
Shall we take this up in the next class?
Yes, so we can take it up tomorrow. Next.
Okay, okay, very good. So please, I have covered a fair bit of ground. I am relying on you to catch up. And I should also warn you that the end semester will be somewhat harder than the mid semester, and there will be a few questions that will be compulsory, which will be of a harder nature, which you will have to crack if you have to get a really good grade. So I'm going to need a way of distinguishing people who understand the course thoroughly from those who are kind of following. So, so I will insist that you have mastered the notes if you want a really good grade. I am warning you right now. So if you are just following the classes as they happen and not reading the notes carefully, you will get a reasonable grade. But if you want a really good grade, I expect you to read the notes carefully. Because as I said several times, the lectures are fine, but the notes are the heart of the course. Okay, on that note, let me say bye. See you on Friday, I hope. I'll confirm this tomorrow. Bye.
Thank you, sir.
Bye.
Thank you, sir.
Thank you.